Hi folks, we're going to take a look at page 129, number 16a. So they give us this position function and they want us to show that the acceleration function is continuous at t equals 0. Okay, so let's remember what we have to show for continuity. So we have to show that its value at 0 is equal to the limit at 0 from both sides. So this is why they gave a definition for this position function to the left of 0. Normally we don't consider that, but if we want to have continuity, we need to have some sort of definition to the left. All right, so the first thing I'm going to do is find the acceleration function. Now, I'll split it up into two parts, and the first part's very easy, because if I only consider t values less than 0, well, we know that s prime at t, which is just the velocity, well, derivative of 0 is just 0. So there you go. That's nice and easy. And then if I look at the acceleration function, which is just the second derivative of the position, or the first derivative of the velocity, is equal to 0. So when I'm approaching from the left for the acceleration function, I know it's just going to be equal to 0. The part that requires a lot more work is from the right. So let me now consider what this derivative would look like to the right of 0. So first thing is to find the first derivative, which is the velocity. All right, so use the quotient rule. No big surprise there. So derivative of the numerator is 3t squared times the denominator function is t squared plus 1. Okay, minus the numerator function, which is t cubed, times the derivative of the denominator function, which is just 2t. And all of this is over t squared plus 1 squared. Now, because I now have to find another derivative, it is worth simplifying. So often I tell you not to simplify. Here I definitely will be simplifying first. Okay, and so here I've got 3t to the fourth minus 2t to the fourth. So that's just t to the fourth. Okay, and then the only other term we have here is the plus 3t squared from this second multiplication. All right. Oh, I forgot to square that. So t squared plus 1 squared. Okay, and so now I'm going to find the acceleration function, which is just a second derivative. So now again, I'm going to have to use the quotient rule. So let's do this carefully here. So derivative of the numerator is just going to be 4t cubed plus, so that's going to be 6t. All right, times the denominator function, which is just t squared plus 1 all squared, minus the numerator function, which is t to the fourth plus 3t squared, times the derivative of the denominator function. So here I'm going to have to use the chain rule. So this is my u squared, which is just equal to 2u. So 2 times t squared plus 1 times the derivative of u, which is 2t. Okay, and all this over the square of the denominator function. So that's just going to end up being t squared plus 1 all to the fourth. Okay. Now, the only thing I really care about here is the value of this acceleration as t is approaching 0. All right. So in the end, I actually don't need to simplify this whole thing. If I had to do something more with it, I would definitely simplify and use my old trick of seeing a common denominator, a common factor here, but I actually don't need to do it because let's think about what we need to show. Is it continuous at t equals 0? So the only thing I need to do is check my limit as t approaches 0 from the left of the acceleration. Okay, but what's that function when I'm approaching from the left? It's just 0. Okay. And then I have to determine the limit as t approaches 0 from the right of my acceleration function, which is just given by this thing here. So all I have to do is evaluate this at 0. And I want you to take a look. This first term, what's that give me? If I put in t equals 0, I get zeros. Here I get, doesn't matter what I get here, 0 times whatever this is 0. Okay, and let's look at the other side. Well, I look at all these factors that I have, and look what I have, a factor of t. So when I replace t equals 0, this whole numerator is equal to 0, and I just need to check, is the denominator equal to 0? No. So the limit as I approach from the right is also equal to 0. All right, so therefore, what we've shown is that s prime double prime at t, which is what the acceleration function is, is continuous at t equals 0. All right. So let's just recap. Step number 1 was to realize that because we were looking for continuity where the function changes definition, I had to check the left-handed and right-handed limit, over here. And in order to do that, I had to find the acceleration function. From the left, very easy, just equal to 0. From the right, had to use the quotient rule a couple of times, but in the end, we saw that whether I approach the acceleration from the left side or from the right side at 0, I get the same result. So it's continuous. All right, that's it for this one.